All right, so we're going to continue now talking about the ideas about our solar system. We mentioned in the last video that a concern was how to explain retrograde motion if you have a geocentric solar system. It's actually quite easy to explain if you use a heliocentric solar system and understand it's the result of relative motion. But people weren't there yet. So Ptolemy actually came out with a pretty ingenious explanation of how retrograde motion could happen using what we now call circles upon circles, which is sort of taking a complicated motion and breaking it down into a combination of very simple motions. And so what he did here was he had, of course, circular orbits for the planets, but the planets didn't just follow in those circles. They actually were in a smaller circle, the center of which followed the path of the larger circle. But then the planet was on this little circle. And so what was happening is this planet, like Venus here, was going around in this small circle at the same time that that circular path was going around the Earth. The dotted line here actually shows the result, which would give Mars the ability to sort of loop around and exhibit retrograde motion. So it seems kind of crazy, but it was a very clever and also sophisticated way to explain retrograde motion and to preserve the idea of a geocentric model. It turned out that this idea of circles upon circles also stuck around for a while and caused some problems for later scientists. So this was just one way to sort of preserve the geocentric model and also explain retrograde motion. Ptolemy's model had some positive qualities and negative qualities that we should be aware of. First of all, on the positive side, it was using a more scientific approach because they were making a very honest attempt to match observations to the model. That is, explain retrograde motion with your model. And that's what it was able to do. So that was also a very good positive quality of the model. On the negative side, it did keep the idea of circular orbits, which, because we now realize the planets don't orbit in circles, we can say it's negative, although at the time people didn't really understand that. And the other thing is that it was really complicated. In science, we use this idea of Occam's razor, which you may or may remember talking about in Civ class, because sometimes you do talk about it. And the idea of Occam's razor is if there are two explanations for some phenomena, the likelihood is that the simpler explanation is the one that is actually true. And so Ptolemy's model was sort of not really a good model because it was very complicated. So according to Occam's razor, this was probably not the right solution. Another problem of the model was that while all the sizes and speeds of the small orbits and the larger orbits for all the planets could be adjusted to pretty well match the observations of the sky, as time would go on, that accuracy would decrease, which is simply because the model wasn't correct. They didn't really realize it, but it did cause it to lose some favor in terms of explaining our solar system and retrograde motion. So we move on to the next person who was very influential, which was Nicholas Copernicus. And Copernicus actually did introduce the heliocentric model of the solar system. He wasn't, of course, the first, as you probably read, but he was the first person where he introduced it. He was able to explain in some ways why it was superior, and it became more accepted. There were many qualities that made it appealing. He explained the motion of the sun across the sky was the consequence of the rotation of the Earth. It wasn't the fact that the sun was rotating or revolving around us. He was able to sort of explain or lay out what planets were at what locations based on when we were able to see them. For instance, Mars is always observed very close to the sun, It's either seen right after sunset or right before sunrise, and so he was able to logically deduce that Mercury would be the closest planet to the sun. Planets that were able to be seen at nighttime had to be further from the sun than the Earth. Things like this was part of what made his heliocentric model very good, was because there were so many different observations that he could explain. One of his shortcomings of his model is that he did keep the idea of circular motion. People were so stuck on the fact that they believed the planets had to go in circles, and this would always adversely affect their accuracy over time. He also ended up using circles upon circles like Ptolemy, and because of that, in the end, his model didn't seem that much better than Ptolemy's model because of the fact that it was complicated as well. So it became the competition of complicated models. So the big breakthrough comes with the help of two people, Tycho Brahe, a Danish astronomer, and Johann Kepler, a German mathematician. And so as you read, Brahe was a very good naked eye observer. Kepler was a gifted mathematician. So Brahe had an observatory where he had people making measurements of the sky over a period of about 20 years. He ended up close to his death, getting associated with Kepler, who was able to use these measurements and figure out exactly what was going on with our solar system. How was it set up? How were the planets moving? Kepler came up with 3 laws of planetary motion. First of all, he found that the planets did not go in circular orbits, but they went in elliptical paths, and they were traveling around the sun. So 2 things: circle orbits are not right, and the sun is at the center. The second law, which we'll take a look at in another video, is basically saying that the planets do not go at the same speeds in different parts of their orbit, which was another thing that people had assumed: circular orbits, constant speeds. Kepler proved that was incorrect. And finally, there's one mathematical relationship that Kepler found was true, that the relationship between the period of the orbit and the distance from the sun. So he found that the period squared was equal to the distance cubed. It's a relatively simple expression that we can use, and if you know one of these quantities, period or distance, you can find the other using the mathematical expression. So here's pictures of a circle and an ellipse. A circle has one point at the center, and there's always a constant distance from that central point to the edge. And here's a picture of how we could draw it. That distance is called the radius. For an ellipse, there's 2 special points in the center, which are called the focus points. And if we have a string of constant length that's attached to both of these focus points, and we hold that taut, we can draw an ellipse, which is, you see, a little bit longer across than it is here from top to bottom. So the distance in the long ways is called the major axis. The distance across it, the short way, is called the semi-major axis. Ellipses come in different varieties. Actually, a circle is a special kind of an ellipse where the 2 focus points are at the same location. And as you pull the focus points apart, the ellipse becomes more and more elongated. We can cut everyone a little bit of slack because the eccentricity, which is how we describe how elongated an ellipse is, for the paths of the planets was relatively small. So they actually are very close to being circular, but they're just not quite circular. We'll talk in another video about the first law and the second law. And the third law is a mathematical expression that you can practice solving for. Finally, you should take note that Galileo's observations of Venus and the phases that he saw of Venus also were supportive of a heliocentric solar system. And one last thing that Galileo did to contribute to this whole quest of our solar system was one of the things that ancient people found difficult to believe is that if the Earth moved, how could the moon orbit around the Earth? Like, why wouldn't it just get left behind? Galileo, with his famous telescope, was actually able to observe a very similar phenomena with Jupiter. He was able to see that Jupiter had 4 large moons that orbited around it. This picture is just sort of showing Jupiter and then the different moons and where the locations were. And basically, by observing this, we could say, well, if you can see Jupiter keeps its moons, and we know that Jupiter's moving. Jupiter moved in either model of the solar system, whether you believed in a geocentric or a heliocentric. So if it's possible for Jupiter, it could be possible that the Earth could be moving around the sun and not lose its moon. And that's it for this.